Section: Introduction. In this section, we explore the integration of large language models, LLMs, with evolutionary search methods. We note that recent studies have combined LLMs with evolutionary techniques for both numerical and combinatorial optimization. Our focus is on natural language planning, which we view as a combinatorial optimization problem where we optimize plans based on constraints expressed in natural language. Unlike previous research, we evolve solutions directly in natural language spaces, eliminating the need for formal task definitions that require extensive effort and expertise. We also acknowledge other works that have applied evolutionary search to optimize prompts to enhance performance on specific tasks. For instance, Evo Agent tested their method on the Travel Planner benchmark, evolving new LLM agents for a multi-agent system approach. Their success rate was 7.2% with GPT-4, while our method achieved over 95% with Gemini 1.5 Flash. In our approach, we evaluate solutions using program-based evaluators during the evolutionary search. This method of integrating execution-based evaluators has been widely used in code generation, where feedback from the execution environment helps the LLM correct errors in generated code. Other studies have explored using learned verifiers and self-evaluation for refining responses and improving model learning. However, we recognize that these feedback mechanisms can be noisy and unreliable, so we plan to address this in future work. We employ a genetic search strategy in our method, Mind Evolution, which combines an LLM with a specific set of prompts to efficiently search for solutions to natural language planning tasks. Before detailing Mind Evolution, we provide a brief overview of language-based genetic algorithms. Genetic algorithms are inspired by natural selection and evolve a population of candidate solutions toward higher quality individuals based on a target optimization objective, known as the fitness function. Each candidate has a genetic representation that can be mutated and recombined. The process starts with a population of solutions, and in each generation, we evaluate the fitness of each individual. Candidates are selected for reproduction based on their fitness, and through crossover and mutation, we create new solutions for the next generation. Over time, the population's fitness generally improves as fitter parents are more likely to be selected. To maintain diversity, we introduce an island model, where distinct subpopulations evolve independently. Solutions from one island can migrate to another based on fitness, and low fitness populations can be replaced with stronger solutions from the global population. This model has been effective in recent successful efforts. In our language-based genetic algorithm, candidates are represented in natural language, allowing us to leverage the LLM's capabilities for effective recombination and island reset operations. Mind Evolution's design includes specific choices for selection and migration operations, a set of prompts for initialization and recombination, and a fitness function to evaluate solution quality and provide feedback. We repeat the evolution process until we find a valid solution or complete a set number of generations, after which we return the best candidate. For fitness evaluation, we implement a function tailored to each problem domain, parsing and evaluating candidate solutions programmatically. This function serves three main purposes: scoring solutions based on the optimization objective, verifying if solutions meet constraints, and providing textual feedback. For example, in the meeting planning task, the evaluation function assesses a proposed plan based on constraint violations, the number of valid meetings, and adherence to the required format. Our empirical findings highlight the importance of textual feedback, as shown in our ablation study. We also note that while verifying solutions can be easier than solving the problem, having an evaluation function does not equate to solving the task itself. Section Summary. In this section, we explore the integration of large language models, LLMs, with evolutionary search for natural language planning, emphasizing the evolution of solutions in natural language rather than formal representations. We describe our approach, Mind Evolution, which utilizes a genetic algorithm framework to optimize solutions through a structured evaluation process, leveraging LLM capabilities for effective recombination and feedback. Section: Population initialization. In this section, we outline our approach to population initialization and refinement. For a given problem, we independently generate a set of initial solutions by prompting a language model with a description of the problem and any necessary information. If we have more than one sequence, we evaluate and refine each initial solution through additional rounds of a process we call refinement through critical conversation, or RCC. This results in a total of candidate solutions that form the initial population for the first generation. In the RCC process, we create a dialogue between a critic and an author to enhance the solution. The critic reviews the candidate solutions, interprets feedback, and suggests improvements. The author then proposes a refined solution based on this feedback. We have found that the critic's analysis significantly boosts performance. For selection, we use a Boltzmann tournament method, where we randomly choose a number of parents based on their fitness scores. This ensures that better solutions are more likely to be selected, while still allowing for diversity. We combine crossover and mutation into a single step, where we improve a set of parent solutions using the RCC process. We sample a number of parents, incorporate their evaluation results, and then apply the critic to propose a revised solution for the next generation. If we have multiple sequences, we continue refining each child solution through the RCC process. Each generation adds new child solutions to the island population, removing duplicates. During migration, each island evolves independently until we clone the top solutions from one island to the next. This cyclic migration helps speed up the overall evolution process. We perform an island reset every few generations, where we select top performers from the global population and retire the lowest scoring islands. We explore two methods for selecting top performers: directly choosing the best candidates or first selecting a larger pool and then using the language model to pick diverse top candidates. Our studies show that the latter method yields better results. Finally, we evaluate our approach on 3 benchmark natural language planning tasks, including trip planning and meeting planning, while omitting tasks that can be easily solved by enumeration. Implementation details for each task, including prompts and evaluation functions, are provided in the relevant sections. Section Summary. In this section, we describe our approach to generating and refining candidate solutions for a target problem using a large language model, LLM, which involves sampling initial solutions, engaging in a critical conversation for refinement, and employing selection, crossover, and mutation processes to evolve these solutions across multiple generations and islands. We also outline the migration of top solutions between islands and the periodic resetting of populations to enhance diversity and performance, ultimately evaluating our method on various natural language planning tasks. Section: Models. In this section, we utilize Gemini 1.5 Flash as our primary model for the experiments. The hyperparameters for applying mind evolution to Flash are detailed in a specific table. We also explore a 2-stage method using the Gemini 1.5 Pro model for problems that exceed the generation limit. This approach is more cost-effective than using the Pro model for every instance. When we apply mind evolution to the Pro model, we adjust the hyperparameters to specific values for better performance. For our comparisons, we evaluate mind evolution against 3 baseline strategies that share the same solution evaluator and prompts. The first is one pass, where a solution is generated in one go. The second, best of n, generates up to 800 solutions independently until a successful one is found. The third, sequential revision plus, proposes 10 solutions and revises each for 80 turns, as we rarely see improvements beyond that. We also include an additional one-pass baseline using OpenAI's O1 preview for reference. We measure the success rate, which indicates the percentage of problems solved completely, separating validation and test sets. We also track the computational costs, including the number of model calls, tokens used, and total API costs, based on October 2024 pricing. Understanding these costs is crucial for evaluating search strategies like mind evolution, as searching is generally more expensive than generating a single solution. For the trip planning task, we aim to create an itinerary that meets flight and scheduling constraints. We divide our benchmark into 320 validation and 1,280 test instances. Our results show that mind evolution significantly outperforms the baselines, achieving a 96.2% success rate on validation and 94.1% on test instances. The two-stage approach even reaches 100% on validation and 99.6% on test. We observe that the task's difficulty increases with the number of cities, and mind evolution's advantage grows as this number rises. In the meeting planning task, we schedule meetings to maximize interactions while considering availability and travel constraints. Unlike the trip planning task, not all meetings can be scheduled, making it harder to determine optimal solutions. We allow searches to continue until reaching iteration limits, splitting instances into 500 validation and 500 test cases. The results again show mind evolution's strong performance, with an 85.0% success rate on validation and 83.8% on test. The two-stage approach with the Pro model achieves even higher success rates. We find that mind evolution maintains a significant advantage as the number of people to schedule meetings with increases. Section Summary. In this section, we utilize the Gemini 1.5 Flash model as our default for experiments and explore a two-stage approach with the Gemini 1.5 Pro model for more complex problems, demonstrating that mind evolution outperforms baseline strategies in both trip planning and meeting planning tasks, achieving high success rates. We also emphasize the importance of evaluating computational costs alongside success rates to understand the trade-offs in enhancing LLM problem-solving capabilities. Section: Analysis and Ablation Studies. In this section, we analyze how mind evolution performs and how its various components influence its behavior. For scaling, we observe the success rate of mind evolution across planning tasks as we increase the number of generations. Our findings indicate a consistent improvement in performance with more generations. We also compare mind evolution scaling to baseline search methods by plotting the success rate and average task evaluation scores against the number of candidate solutions generated by each strategy. The task evaluation scores penalize unsatisfied constraints and suboptimal outcomes, with the best possible score being 0. We further explore cost-benefit trade-offs related to specific API costs in our additional results. Our results show that success rates and average task evaluation scores improve steadily with more proposed solutions across all methods. Notably, mind evolution outperforms baseline strategies in terms of the number of candidate solutions required to achieve a certain success rate. We observe that the best of N method underperforms in the travel planner task, likely due to its inability to leverage implicit common sense constraints learned from evaluation feedback. In our ablation studies, we examine the contributions of different components of mind evolution. Our findings reveal that the critic step in the RCC process and textual feedback from evaluation functions are crucial for performance, although other components also contribute meaningfully. We delve deeper into the trip planning task, particularly in a challenging setting with 10 cities, to highlight performance differences. Our analysis shows that including the island model in the evolutionary search significantly enhances mind evolution's performance. We also compare the effects of increasing candidate solutions per generation versus having more generations, finding that deeper evolutionary searches are beneficial while maintaining broad exploration in each generation is also important. We introduce a new challenging task called StegPoet, where a hidden message must be encoded into creative writing. Although this problem is complex, it can be verified programmatically. The hidden message, represented by a sequence of numbers, should be embedded in a creative text like an essay or poem. We require a number-to-word substitution cipher and generated text that uses this cipher, with an additional constraint on the average number of words between cipher words. The difficulty of this task increases with the length of the hidden message, the repetition of numbers, and their proximity to each other. We empirically find that as the mean distance between cipher words increases, the task becomes more challenging. We split the problem instances into validation and test sets. Our detailed performance results show that the two-stage mind evolution achieves 87.1% on validation and 79.2% on test, while best of N only solves 1% of the validation tasks.